yourselves, both of you, and yeah, I'll let you guys go. Thank you.
Thank you, Jason.
Yeah, no, thank you, Jason. We really appreciate Dan giving us a chance to go ahead and have the presentation. And thank you, folks, who are attending this. I am Shivani Weiss. I'm Technical Services Engineer with Odessa Separator. Have been with the company for about over 3 years, and I'm really glad to be presenting today's topic, which is how to improve the performance of downhole desanders along with the test results and analysis. Along with me, we also have Luis.
Good morning, guys. Like Shivani said, thank you very much to Donan for giving us this space. My name is like Shivani, Luis Guanacas. I am technical service leader in the company. I have been working with OSI since 2015, 5 years now. And then this is a really exciting topic. We have been facing really difficult questions about this technology since we started to distribute this tool, and now we finally made a experimental setup and computational model to come up with all the answers that the customer requires. So thank you very much for being here.
Perfect. Well, so what we're going to go ahead and cover today is obviously what is the causes for sand production, what are the consequences that this sand production does have, what are the control or the management tools for the sand control, and how does the downhole desander works, the operation efficiency parameters, and the wells that are optimized, and at the end, go ahead on all the conclusions with all the discussions that we've had and how do we at the end optimize the well which has so much sand production. So let's jump right into our own basin, the Permian Basin. Like we can see in the picture how closely the wells are placed right next to each other, and that definitely shows us what is the well spacing here in the Permian Basin. And this has been a trend, I would say, since 2017 that the operators have started downgrading their well spacing. I believe in the Delaware Basin, the average well spacing went from about 979 foot to about 675 foot, and we saw the same trend in the Midland Basin, which went about 675 to about 545 foot. And that's what is one of the things or the main causes of where we have the parent-child interaction problems. Also, one of the main reasons for the sand production. Obviously, in the Permian Basin, our Wolfcamp shale play, that's one of the longest that's been drilled in the Midland and Delaware Basin. We've had about more than 4,000 wells drilled on this Wolfcamp shale formation, and that's also one of the tightest formations where, along with the rock itself, what we now have to do is having done conventional wells, increasing the lateral. That means having to increase your frac sand, another factor that goes ahead and causes the sand production problems. Let's go ahead and see when we're talking about conventional well versus unconventional well and what's the sand profile. So we can see on the conventional well, whenever we're having the plastic hole deformation, once it's done, and how does the hole stabilization happens over the lifespan of the well, and now with the decline of the reservoir pressure, there's going to be some increase on your sand production. Versus your unconventional wells, we can see the trend of your sand production along with the frac hit that, again, depending on how close the well is, the parent-child interventions that we've talked about, and we have that frac hit, probably good for the production, but not so much for your sand production. And that's where we have so much sand come in during the lifespan of that well. And this is a typical well bore for our unconventional well. Well, one of the wells in the Midland Basin itself, where we have about 10,000 foot of lateral. We can see the perforation and the frac stages. And for this one, we're using about 21 million pounds of sand just to frac that 10,000 foot of lateral. So some percentage of it is going to still stay in the reservoir, but how about the rest? And that's what this picture is showing, is we're using this much sand, which is 21 million pounds of sand, to frac this well. Probably now every operator has different percentage of the flow back, but let's say if 30% is the flow back, if we calculated, we're filling up about 2,715 mud joints. So we can imagine how severe is the well that we're talking these days in the Permian Basin, and how severe is this well production.
Okay, now that we introduced the problem, uh, we know there are different solutions that are available in the market to control the sand. And we know the sand can cause problems in surface, downhole, even in the perforations in the reservoir. So this investigation, this study is going to be focused just in the desander, in the downhole desander. So this is the flow path on a typical desander. The fluid coming from the perforations is going to get to the desander typically through an slurry intake, right? Then the fluid is going to flow downward and is going to get tangentially inside the hillets. We get a mixture of fluid and sand flowing around the veins of the hillets, and then those veins are going to cause a rotational movement, right? Then this rotational movement is going to cause a radial force. That radial force is actually the one that causes the separation, because in that moment, when the fluid and the solid leave the hillets, the solid, which is denser, is going to be pushed against the wall of the desander, and then the lighter phase, which is the liquid, is going to be at the middle, and then it's going to be sucked by the suction point, which is in this case the deep tube, which is an inner pipe that you see at the middle of the tool. Like you know, all the sand separated is going to be pushed down into the tail joints. We're going to see that some customers like to use open-end completion, and another customer like to use close-end completion. That's another discussion. It's a really interesting topic. There are believers in each side, but I think it's something that we need to talk about later. Okay, let's move, Chivi, please. This is the experimental setup. As I said before, we use two models to answer all the questions we have. We have the experimental setup, which is this one right here, and we have a computational model. In the experimental setup, we have three tanks. We have a supply tank, which has the production fluid at the bottom with a pump connected to the tank. At the top, we have another tank which has sand and polymer. The polymer was used to simulate changes on the viscosity and then to carry all the sand particles that we want to put in the production fluid. As you see, there is a mixing point where the sand and the production fluid from the supply tank are going to mix, and then they are going to travel directly to the well. The well has this configuration, which is a pump at the top. The pump we used was a peristaltic pump to simulate the reciprocant movement of the beam pump. We used a descender, our descender, and we had a tail joint set up below that. As you see at the bottom, we have a push valve, and then we have the storage tank, which is gonna cache all the production fluid. This is basically how we set up everything. Now, the separation efficiency is going to be measured with the sand we found in the tail joint. And then we are going to measure the sand on the storage tank, on the tail joint, some on the rat hole, and we are going to compare that with the amount of sand we mixed at the beginning in the mixing point. Okay, let's move, Chivi, please. This is one of the experimental setup we made. I would like, guys, for you to take a look and see how the tool works in the real life. So if you see the sand and fluid are gonna meet in the mixing point, then they are gonna get into the desander through the intake. In this case, the intake is on the screen. You will see how after the fluid pass through the helix is causing this rotational movement, right? And then at the bottom, look how all the sand is being concentrated at the bottom of the tail joint. And then close to the helix, close to the deep tube, you will see the vortex. Maybe it's not really clear, but you can see close to the helix the vortex phenomenon sucking the fluid inside the deep tube. That's what is happening downhole. That's the effect or the science behind this technology downhole. So, what is it important for you to know how much is the separation efficiency of this tool? Well, it is important because with this information, you will know what is the amount of sand that you are going to control or separate with your descender, right? That will allow you to know how much sand are you going to see in your pond and what is the size of the sand particles that is going to be affecting or maybe going through your pump. This information is really helpful. It can help you to size your plunger feet, right? To maybe check for additional components, and it's really important to be realistic when you are running certain sand control or whatever technology you are using in your well. It's really important for you to know what can you expect from this technology and what is the capabilities of the technology. So to optimize this technology will help you to extend the run life of the equipment. You know that is directly related with the time in production. That will give you possibilities to increase the production rate, and economically will help to the cash flow of the project. Less intervention, less failure. It will help to the current economy, which is pretty tough these days.
Hey,
Let's
Luis,
move. Yes, sir.
I have a question.
Yes, sir.
So, it's not necessarily for me, because I don't have any oil wells, but I'm just trying to maybe speak at least to sort of any kind of counters at the moment. So the video was very, very nice, and it seemed to be kind of doing what it's supposed to do. But I wonder, if I'm an operator seeing that video and I thinking to myself, well, that tool looks nice and it seems to work there, but the solids that I'm dealing with are much, much thicker and much heavier. I mean, does it still work with, so like, is there a point where, the solids are too rough or, how do you get around that, I guess, is sort of the first question, though, if you're dealing with much thicker solids.
Okay, well, we will cover this part later, but that has more to do with the distribution size of your sand, right? Uh, in that section, Chivan is going to elaborate more, but just to give you a heads up, big and fine particles plays an important role on this separation matter. Uh, but this is like a parameter that we hardly can control. Nowadays, all the companies are using 100 mesh, maybe 30, 50 frac sand, and then this size are going to play an important role in the dynamic of the separation in this tool.
Okay. So you'll adjust depending on the solids then.
Right.
Yes. Yeah, we need to.
That's a great question. And to champion what Luis said, that's exactly what sets us apart is there's not one size fits all. It's definitely by doing this lab test, doing the analysis is depending on the solid size distribution is what we're going to go ahead and size it up. It's what is going to be the area between the veins that Luis was talking about is going to create that centrifugal force. Depending if the particles are much coarser, like you were talking about, we would have to adjust it and design it accordingly. Versus if the particle size is really fine, like 100 mesh, we'd have to go ahead and adjust that centrifugal force creator accordingly. That way, that separation is created, and that's what is critical in this point.
Correct. Yeah. Yeah. We will talk about this just
yeah, and we
later.
have
I
like
jumped the gun. Apologies. Keep going, guys.
No, don't worry. That's good. That's good to have the discussion. But after we talk, you can give us maybe your feedback or your input about it. So looking for find the parameters that really impact in the operation efficiency of this tool, we analyze this tool from different perspectives, right? We analyze the design of the tool covering the helix angle, the jetting area, the helix size, the tool length, the material that we use, and the type of intake. We check the fluid properties, viscosity, density, contrast. We check the production parameters, the pumping speed mainly, and then the fluid rate. And like you were asking, Jason, we cover what is the impact of the particle size distribution, the PSD, in this tool. So are going to get in this topic right now.
So continuing on the Desander itself. So the internal part of it is going to be your helix. And what is the helix angle and the jetting area? So for example, let's go ahead and see we have your Desander, we have the vortex sleeve. And so let's say these are the two helixes that we're talking about. These are the ones that create the centrifugal force. So we can see, for example, this one is going to be your 1.1 helix, and we can see what is the area in between this angle versus this is 1.4, and we can see what is your area between these two vanes or angles that we're seeing. And that's exactly what differentiates on creating that centrifugal force. So that's what it's saying is your jetting area is this one, is what's going to make that difference, and this is your vane angles on every helix that's inside your Desander. So your jetting area is going to be one of the ones that creates the most difference on how you're differentiating the particle. The smaller jetting area, the more efficiency you're going to have, versus the simulation on helix angle that we had is you have your 1 degree versus 10 degree. You can see it does not make much of a difference. It's almost the same on this one. And then again, once we do have the helix sizes, is we would want to have what is the optimal production range, is depending on the particle size and the production is what would be a range that the production does stabilize. For example, let's go ahead and see in the 400 microns, the red line, once we do have the 2.3 helix, what is the optimal size that we can range it? Here we can see that it stabilizes in between 150 barrels of fluid per day to about 220 barrels of fluid per day. Versus if we have the same in 2.4 helix, that is 1 notch higher with a little bit of that more jetting area and that angle twisted, what's going to be your optimal production range is going to be starting from about 210 going to about 305 to 310 barrels of fluid per day. And that's exactly is the BHA. That's what it's showing is you have your pump, you have your sitting nipple. Right below is going to be your intake, and then you're going to have your Desander. So this is where the fluids would come in, go inside. This is going to be your helix. This is the critical point that creates your centrifugal force. And once that force is created, you're going to go ahead and separate that solid particles, dump into the tailpipe, and your cleaner fluid goes into the dip tube inside your pump. And depending on the helix sizes and your tubing size is what we have that helix size and what do we want to go ahead and size it up, what is the well history or well intervention, what is the solid size particle that we're looking at, all those factors to come in for sizing that helix size. And for example, this was the 1.4 that we saw. 1.4 means that we're dealing with 2 and 3/8 tubing versus 2 point something is 2 and 7/8, 3 point something is 3.5 tubing. And then obviously the sleeve length. Also, this is one of the things that we realized over the years, especially over the couple years that we've had horizontals, we've had conversion wells where we're still seeing the frac hits, where we're still seeing high solid production, and trying to analyze does the 2-footer sleeve is sufficient for all the solids that coming in, because we can see like here if the sand rate is less than 200 mg per liter, we can see that your sand rate or the radial force is about 4.5 to 5.5 inches right below that vortex, versus if we have a higher sand rate, where is that radial force that comes in? And when we mean by radial force, as if you all might have seen the sand cutting, is exactly what's happening, is how do we control that? So one of the parameters that we've come along is how about if we go with a longer sleeve length, does that help in controlling that radial force and protect that sand sleeve itself?
Well, in this part, the analysis was focused on the materials. The materials are very critical, like Chibi was explaining before. There is this centrifugal force, this radial movement that is causing an acceleration in the particles. Depending on the size of the particle, if it's fine particle, if it's a very coarse particle, that's gonna has a different acceleration in the system. If you take a look to the graphic on the right side of the screen, you will see a simulation we made in our computational flow dynamics model, where you can see that right after the fluid passed the helix, around the helix, we can reach a flow velocity that 200 feet per second. In different numbers, we will see that in this point, the velocity of the particle is going to be like 110 miles per hour in the tool. So that velocity is going to cause an impact of the sand in the surface of the tool. So this is simulated by a sand penetration rate model that you can see right there. This penetration model, it analyzed basically the sand production rate and penetration factor, analyze the material, and then the purpose of this analysis was found the right materials for the specific conditions, right? What's the problem when you don't use the proper material for your tools? Shivani, can we move, please? You will have this problem. So these are real examples of how this velocity is affecting the inside of the tool. So you will see that you have low penetration cases, but at the bottom, you will see a high penetration rate affected together with a corrosion problem. So when you don't size, when you don't use the proper material for your downhole conditions, you will have this result. And if we combine this problem with the sleeve length that Shivani just talked about, we will have two problems, because normally the tailpipes are weaker than the sleeve that this desander used. So when this centrifugal force is moving down and reaches that tail joint, the first tail joint below the sleeve, you will have sand coating in the tail joint, and probably you will have a fish problem. So it is very important. We made the simulation. We use finite element analysis, FEI, to check the impact of these velocities of these acceleration rates in different materials, and we come out with this nets table. This table summarizes in what conditions you can use different materials for different components of the desander. For instance, materials like carbon steel can be used in low corrosion, low erosion rate environments. So this is very critical. In order to optimize, to achieve longer runtime, maybe if your well is in the stabilized zone, like Shivani explained, we can use probably this material. But if you're expecting really high penetration rate or really high sand production, I'm talking about higher than 200 milligrams per liter, I highly recommend you to move to a different and more like a stronger material. So plastic coated. The plastic coated was evaluated and we found that this material is probably really good in moderate corrosion environment, but low erosion rate. So it's important to keep this in mind. Nickel plated as well. We can tolerate moderate to high corrosion, but still low erosion rate. And the most common stainless steel material, it is for high corrosion, but we need to be careful. Low erosion rate have to be the one in this material. Now, based on this result, we work with a different alloy. We didn't develop this alloy. We just found a supplier who provide us a really special alloy material, and we proved this one with our finite element analysis, and we found that this material is really good in high corrosion, high erosion rate environments. So for new wells, new completion wells, or wells submitted to very frequent frac hit, this should be the material that you should use because it's high resistant. It will give you a longer runtime, longer production period, and you'll be really, really impressed by the result you can get with this type of material. Okay, Chibi, let's move. The next one, we analyze the type of intake. You know, you can see out there in the market that desanders are made on perforated intake, slurry intake are the most common, and then a different one which is the screen intake. We check the different type of intake and we analyze the efficiency of each one. You can see in the vertical axis the efficiency of the tool, and you can see on the horizontal one the particle diameter. So if we check first the slurry and perforated one, which is the gray and blue lines, you will see that those are very close. I mean, there is not much of a difference in the performance of a slurry that perforated desander. We will find that it matches each other, so it's really close. But we found a really huge difference when we use this screen intake. Why this happened? We got different theories about it. We think that could be because the intake is closer to the hillets and then the acceleration point is closer. We are not going to lose pressure close to the hillets. Could be multiple reasons. This is a different whole analysis than we need to make in the future. But if you take a look, you will see that in the fine material particles, you will have a differences in efficiency between 50%, and in the medium-sized particle, the differences in efficiency is like 15 or 17%. So it's really good. The performance that we get with this screen intake tool was much better than using the perforated and slurry one. Now, previously, we talked about the variables that we use in the design of the tool. Those variables are in our control. I mean, you can choose the material, like Chivan explained before, you can choose the hillet size, and you can decide what kind of intake you want to use, right? But this one, the fluid viscosity, it's barely you can control it. At least you're maybe using different recovery methods with solvent or chemical chemical recovery, but otherwise you gotta deal with this, how it's coming from the formation. And the graphic that you're seeing right now, it is very, very indicating. You will see the efficiency on the vertical side and the viscosity on the horizontal axis. Now, if you are dealing with low viscosity fluid, you will have an optimal performance of this tool. If you will see, let's say that we have medium to light oil, we will have a efficiency between 55% and 100%, which is really good. However, when we move and we go to really heavier oil and then more viscosity, we will see how drastically, for the same rate and the same particle size, the efficiency is going to drop drastically. So this is a parameter that is going to affect really, really, really high on your Desander performance. So it's really important for you to analyze each case and check how is the oil that you get downhole. This is another factor that really plays an important role, and this is really close to the question that Jason asked, and it's really close to the information that Shivan is going to explain next, and it's the density contrast. As higher is going to be this contrast, better is going to be the separation efficiency. Then, if my particles are bigger, my efficiency is going to be better. That's like the close relationship. So the liquid is going to be dragged by the differential pressure that you're going to have at the middle of the helix. But my solids, which is the heavier phase, they are going to be submitted to the radial force and they are going to be pushed by this force to the tail joints. So Shivani will talk more about this real quick. Uh, Finally, this is another parameter that you can control, which is the pumping parameters. They played an important role in this matter too, and that's what we found. If you take a look to the graphic on the left, you will see the speed of the pump, the velocity. So the velocity, the pumping speed, has a direct relation with the separation efficiency. As higher velocity, you are going to have a greater efficiency, right? So that's important for you to consider what is your pumping speed, check the solid size that you're producing, and then play with the helix size, which is the graphic on the right side. We play a little game in this graphic. You will see two lines on this graphic. You will see the red one and the yellow one. And the yellow one, we use these productions and then we size the proper helix size. So based on the results we get from the previous analysis that Shivani explained before, we choose this specific helix size and then we measure the separation efficiency. As you see, the yellow line shows really good results when you use the appropriate helix size. However, in the next scenario, we use an oversized helix, a bigger one. And then you see how the efficiency drops like 50% in all the cases. So that tells you how important for you is to size the helix with the appropriate size. We normally recommend you to check maybe the productivity index of your well or check your pump capacity and make sure the reservoir capacity is going to match with this pump capacity. Sometimes we use the pump capacity to size the helix size, and in the reality, they will never match that pump capacity, and we start producing less and quite less that the size that we use, and of course, we see the results. No very good performance and low efficiency. That's really important to match those two ideas, the productivity index or the reservoir capacity with the pump capacity, so we can get the proper match and get the proper helix size.
And then one of the other things is obviously the one critical thing is the particle size distribution. And I'm really fond of this picture because this exactly shows us whenever we're talking about, we've heard this, we have such fine sand, we have such fine frac sand, 100 mesh, and I'd like the tightest sand separation that you would have. Versus that's actually not the case when we see downhole, the same micron size, when we have mixed with your fluids, that's oil, water, does go ahead and swell up, and that's what goes in the downhole. And that's exactly we might have seen in a teardown. Whenever we're tearing a pump, we're not going to see particle by particle that we see. It's actually the chunk of particle that comes in, and that's exactly what we're talking about, having to go ahead and separate this versus having that final particle. So understanding the right balance of the viscosities, the densities, the fluid API that we're talking about, and how does this go ahead and swell up and go downhole is what is the actual condition that we're separating. And that's what it would give us a better idea of this is your particle size distribution. Now, this is once we have collected the sand, probably from the tailpipe, we go ahead and dry it up and have it go ahead and distribute and see what is the micron size depending on every sieve that's there to see what is the retention weight of each sand particle size. And that's what we would get. Okay, this is the particle size distribution that goes in this well. And that helps us a major factor to decide what kind of separation or what is the right size determination moving forward of your helix angle, of the length of the desander, of the stages of the separation that we're talking about. And also the viscosity, like Louis was talking about, is exactly what we can see is, let's say, we're talking about 800 microns. And now we're going about 50 centipoise. We can see what is the efficiency that we're talking about is 40% versus whenever we go to 1 centipoise or 20 centipoise, how much does that separation efficiency increases that we're talking about the same particle size distribution. And then this is another parameter. So this is what we have, the particle size distribution. We can see we've had the sand sieve analysis, then we can see what is the sand size in every slot that we're getting. So we can see the percentage of the 12 slot, 10 slot, 8 slot, 7 slot, and then pen is anything that's finer than the 7 slot size that we have in the sand sieve analysis. So now this is the one that we took before using the sand control. So in this one, what we did find out that we have, this is your particle size distribution, and how do we go ahead and size it up? So in this particular case, what we did is we did a 2-stage filtration where we had screen intake as an intake of the fluid, and then we have our downhole desander. So even though we can see that the size distribution does show a lot of finer size particle, going back to what we just saw, the downhole condition and the particle itself aggluminating, we went ahead and chose the 12 slot sand size to go ahead and separate that first stage, and then everything that's finer is going to get separated by the centrifugal force created by the helix and get dumped into the tailpipe. So now, after we've designed this, whenever we did get a chance to go ahead and get the particle size once it was installed in, this is what we got. So we have the particle size distribution, which is everything that's fine sand from the tailpipe. This tells us two things. That first stage is the 12 slot size that we've used, right? So everything that's bigger than 12 slot is not found in the tailpipe, which means that your first stage filtration or your sand screens are doing its job. And second thing is all the finer particles are found in the tailpipe, which means that the helix is creating that centrifugal force, which means your desander is performing its job. And this definitely gives us a better idea or a confirmation that two stages are doing its job and it's working just the way it's supposed to. And this is an example of all the wells that's been optimized. We can see the one that's used without a desander versus the one that's been used after the desander, and how much of the runtime difference it's made, and average is almost gone to about 40 to 50% in all the wells that we've done. One of the critical things that we definitely believe is, yes, it is sand separation, but understanding all the parameters. Every well is different. We do have very common usage of the frac sand that's been using these days, but the well history itself, what is the parameters that working for that well, and designing is something that we definitely believe in, trying to see the root cause of the problem and then analyzing all of that and adapting it to have that sand separation system is something that does make us more efficient.
Yeah, that's really important. The other really good conclusion we get from this analysis was from the parameters that we can control, the one that we can make and decide about it. The pumping speed and the downhole desander design were the one that made more influence on the separation efficiency. When we use run design, or you choose a really inappropriate design, you can lose between 40 and 70% of the separation efficiency, or in the worst case, you can reduce the run life of your pump. So that's really important to know.
Yeah. Another thing that we realized that we've talked about is the helix size, the jetting area, the tool length. Obviously, once you know that how much is the sand rating that's happening, where is that radial force that's happening, what is the materials that Luis covered on, what is your erosion, the corrosion, all of that parameter does give us a better idea of what is a good vortex desander to be sized on this well.
Yeah. In addition with that, we saw how the type of intake that you use is going to play a really important role in the design. As you see, the best result we get when you use the screened intake. And then something that you need to pay attention really close is to the information that Shivani was giving us at the beginning of the particle size distribution section. That particle size distribution is going to change downhole. It's not as clean and as pure as you see that surface when you do the SIF analysis. So it's really important for you to be aware of these things. Options that we have seen in the engineering side is do wet SIF analysis, or maybe find different parameters to check the real distribution of your sand.
Yeah, and then on addition, obviously your densities, the viscosities, this is something that's not under our control, but having known that factors that does contribute to your separation efficiency does give us a better idea of what if we do need to size up that helix a little bit more. That way, if the fluid is much denser, the viscosity is much denser than what it's in the Permian versus in Colombia where it's there, or North Dakota, that's what gives us a better idea of what is the right size on it.
The factor that we found, and this is a really common question in all the meetings and presentation we had, is what about the angle? What is the angle? And then many customers has asked about which is the angle of this helix, but what we found was, despite how you change the angle, if it's severe or if it's not really severe, it didn't impact really high on the separation efficiency as it does the jetting area. So angle is not a really drastic parameter.
And then one last thing is, obviously, again, your particle size distribution and how efficient is the separation system that's downhole Not only that, now everything would change according to the sand rate that's been produced on the well, the sand distribution that's been on that particular well, what is the frac hit that they're expecting, what it's going to go ahead and do. So there's not a certain answer depending on just particular well is what the design factors would change. Yeah, and we're open if there's any questions at all.
I don't have a question, but I just wanted to say thanks for taking the time to talk about this a little bit, too, and providing your contact info. And please, folks, take a snapshot or take that info if you guys want to reach out to them for more.
Yeah, no, absolutely. Oh, go ahead.
Yes, Guy, thanks for such a great presentation. I just have a couple of questions for you, if you don't mind. One of them is you were mentioning that you size the screen based on, of course, what you're expecting and try to make let's say, a primary separation on the screen before all the fluids and solids get to the desander. But is the length of the sand screen adjusted based on the expected flow rate in the well? Because I'm concerned about having enough area enough flow area in the screen.
Absolutely. Yes, great question. Yes, it is adjusted, and more than so, what is also adjusted is, like you said, the area is the slot size. So every slot size that we're talking about will contribute to the pressure drop. That's going to be an important factor here. So let's say we're having certain fluid rate, we're having 200 barrels versus we're designing for 600 barrels. And what is that slot size when we're going ahead and contributing it? If we see that the pressure drop is much higher on an 8-footer sand screen, we might want to go ahead and have a 24-footer or have two 24-foot screens. That way, the most important is we're controlling that pressure drop and controlling that area. So that definitely plays a factor. And every time we do the simulation, we always have the well factor, which is the safety factor, which the well is the moderate, if it's severe, or it's a high condition. So we can see if we're using the length of 2 screens versus 1 screen, what is the optimal rate that the screens can handle, and what is the optimal rate that the well is showing us. And if that does not go under the optimal rate of the well, we'll go ahead and size it up.
Thanks, Giovanni. That answered perfectly my question. That was my assumption. Another question could be related to the amount of joints. I'm not very familiar with the completion at the early stage after the fracking when you install the pumping system. So usually how many tail joints do you have below the pump, just like mud joints, to keep this? Is there any kind of dumping mechanism for that, or just a brief input about it?
Well, again, that would definitely depend on the sand rate and how much space do we really have in the particular well. But a rule of thumb that when we're using a desander, and we do know that this mechanism is to go ahead and dump your sand particle into the tailpipe, we do definitely recommend at least 3 tailpipes below your desander.
Good.
And then this is like adding a little bit to this answer. It is like this is one of the advantages of using the screen. Giovanni mentioned that this number of tail joints is decided based on the sand production rate, which is really accurate. And then if you have a specific production rate, sand production rate, and you're using on the screen, you're going to split that production rate between the rat hole and the tail joints. So typically when you use this system with 2 stages, screen and desander, you don't have to run smash tail joint as you have to do with a desander, because in the traditional desander, all the sand is going to be directly to the tail joint. So correctly. So you can simulate that. We can simulate the number of screen based on sand production rate, runtime expected, and a different parameter, and we can tell the customer this is what you need. But of course, if you are splitting the initial sand production between the screen and the desander, you will have much less of tail joints below it.
Thank you. Do I have time for a couple of more questions?
Yeah.
Okay, good. You mentioned you used a peristaltic pump to simulate the pulsing pumping motion of a rod pump.
Yes, sir.
Is this product also intended for continuous pumping flow, like a PCP or an ESP of a low flow rate?
On that scenarios, we will have to use better a centrifugal pump. A centrifugal pump. I mean, it can like match higher production rate, but the reason of that pump it was just the simulation or like kind of copy the reciprocal movement of the beam pump. But if we are using centrifugal pump like ESP or we attempt to simulate PCP, it's much easier for us to use centrifugal pump instead of the peristaltic pump.
And to champion what Luis said, yes, we do have case studies where it's been pretty much of an efficient separation rate on your ESPs, let's say centrifugal force, and how two-stage has worked much efficient whenever we have that first artificial lift system go right in and produce that much sand, and how efficient that two-stage has proved us.
Well, I'm glad to hear that. So the product is not only intended for rod pump systems, but also for different artificial lift systems.
Just
Pump.
these are our focus is on this particular application, but we do have application that is for much higher rates and much higher continuous pump on ESPs too.
Okay, my last question is, have you seen any gas separation benefit related to when you use the Desander, because you kind of have some separation there? So have you actually seen an impact on this gas separation? Have you had a chance to do that, to see that?
Well, so two things. We go ahead and use the screen. Let's say if we want to go ahead and have it as a gas separation, what we do is we go ahead and have it for a 50 or 75 slot. Now, what it's going to do is primarily, it's not going to act as your sand separation, but it's going to act for homogenizing your fluid. Because whenever you have that restrained intake, you do have that coalescence effect of your gas going out before it goes into the intake of your pump. And yes, as far as the desander goes, it does give a one last chance to separate that centrifugal force that's created before it goes into your dip tube. So primarily, desanders would not be as much effective, but if we do go ahead and have tweak the application, have the sand screen around it, that way it does have much efficient benefit on separating the gas. It does have a beneficial aspect to it.
And then adding a little bit about that, it's of course the reverse flow, when the fluid change the direction, it will give you, like Shivani says, some gas separation. But like in this case, we are not giving enough space area between the dip tube and the housing of the desander. That will reduce the separation capacity, the gas separation capacity, if we want to say something. But on these cases, when you're looking for use desander with gas separation, we can combine that with an oversized body and then take the advantage of a bigger chamber to remove the gas separation and use the gas venting port at the top of the system. So we will have a gas separation system combined with the desander.
Yeah, that's a great point. So all the tools are just like the Lego pieces. Just to go ahead and give you a better idea, is what we can do is combine, let's say, your desander with a gas body. So you are promoting that gas separation along with the solid separation. So we can mix and match whatever is the well requirement on it.
Great.
Little
Thank
Lego,
you.
little Roblox.
Jason, what were you saying?
What was that?
I said, it's kind of like Legos or like Roblox, I suppose.
You're right.
Yeah, correct.
Yeah. Yeah, no, thank you for the questions. We really appreciate
Yeah,
it.
thank you very much.
Yeah, no doubt. I mean, like, look, I know everybody looks at everything new, or maybe something is with a healthy dose of skepticism, everywhere along the way, because people are making big decisions. They want to make sure that, something's going to work for them, though, too. Definitely, right. So,
Sure.
Correct.
well, guys, appreciate the time. Please, we'll have to do it again another time then. So.
Sure. Yeah. Thank you
Yeah.
again, Jason. And thank you, folks, who attended the webinar. If there's any questions that we can help, please feel free to contact us. And have a great rest of the week. Thanks for the time.
Thank you very much, guys. Have a good day.
Yes,
Thank
enjoy
you.
the day.